Hey, good people. I want to show you something cool today. This is not going to be on a quiz or anything, but I think you'll like this. So I'd like you to try to do this with me. Um, Go find a pen and a piece of paper. You can pause the video, come back. All right. I want you to write down this number on your paper. Write it down right at the top. 1.618. Okay? Next, what I'd like you to do is to choose two random numbers. You can choose whole numbers. Um, You can use whatever method you like. You can ask a sibling or your parent to give you a random number, or you could roll a die. Uh, you could do whatever you want. Okay, so I'm choosing two random numbers. I'm going to use my calculator too to pick one. I have a random number picker. Alright, so I picked these two numbers. Alright, next I want you to write down those two numbers that you just chose, and they could even be the same number if you got the same number twice. It really doesn't matter. You could have gotten 5 and 5, and you just write it down on your paper, okay, separated by a comma. The next thing I'd like you to do is add up those two numbers that you wrote down and write the sum next to them. And then look at the last two numbers you wrote down and write down the sum of those two numbers. So I want you to keep doing this pattern a little bit more than 10 times, even though it's tedious. So we're going to build up this little number sequence here. Starting out with our two random numbers, we're going to add each sum to the previous number in the list. So I just got 149. To that, I'm going to add 75 because that was the previous number in the list. I got 224. To that, I'm going to add 149, 373. And again, I'm going to add that to the previous number in the list, which was 224. And adding that to 373, 970. To that, I'm adding 597. I'm going to do this about 5 more times. 1567. Add to that 970. 2537. To that, I'm adding 1567. 4104. 6641. 10745. And I'm getting tired of doing this. I'm sure you are too. And I'm going to stop right now. 17386. How many times did I actually do this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I did it 12 times. Alright, so what we just did was we added up our two random numbers in a really clear pattern. Each time we got our sum, we were adding that result to the previous number. So 1 plus 74 is 75. 75 plus 74 is 149. 149 plus 75 is 224. 224 plus 149 is 373. And so on. This pattern might be familiar to you. You may have studied it a little bit in middle school. It's not the exact Fibonacci sequence, but it is the way that the Fibonacci numbers are generated. What I'd like you to do is take the last two numbers that you wrote down, the larger number and the number before it, and I want you to divide the larger number by the smaller number. Use a calculator. What did you get as your answer? Wait, that's weird. How did you get that on your calculator screen, but you already had it written down on your paper? 1.618. That is so strange. Wow. So this is weird. I told you to write this down first before we even started the video. And hopefully you did that. And then I told you to choose two random numbers that I had no idea which you were choosing. You added them up 10 or so times and divided them, and then your calculator screen returned the same number that we already wrote down. That's very interesting. Well, this is something that's been studied for literally thousands of years, and it has a name, this number. Just like we call the number pi 3.14159, we call this magical number the golden ratio, and you can Google it now if you want to. The golden ratio has a Greek letter that we also use for it, the Greek letter phi, and if you want to be more exact, you could say it's 1.618033989. It goes on infinitely just like pi does. And this number has so many cool properties. I could literally talk about this for about 3 hours, and I still learn new things about it every year. So I want to show you at least how to derive this number and where it comes from. I feel like the cool thing I already showed you, but you could learn a little bit more about it if you watch the next 10 minutes, but I'm not requiring you to do so. But if you want to delve in a little deeper with me, feel free to do that. We will learn more about this as the year goes on, but this isn't really quite algebra, although I will use algebra right now to derive it. The most simple way that this is usually defined, and I think the earliest way it was defined, is you take a line segment and you divide it into two pieces, a big piece and a small piece. And you divide it in such a way that the ratio of the big piece to the small piece is the same as the ratio of the entire length of the whole line segment divided by the big piece. And we usually call the big piece A and the small piece B. So we try to set up this ratio in such a way that the length of the bigger piece to the smaller piece is equivalent to the length of the whole line segment to the bigger piece. And this is usually read as A plus B is to A as A is to B. This, if we can set it up this way, this is called the golden ratio. A plus B is to A as A is to B. I could show you what that looks like right here, this little demonstration. Right now it's not set up that way. You can see that the ratio of A to B is 2.49 and the ratio of A plus B to A is 1.4. But if I adjust the way this is set up, I can actually get it to where they're equal. Let's see. And what do you know? They happen to be equal at 1.62, which I think you realize by now is really close to that number that's written on my calculator screen, 1.618. And it turns out that this geometric property happens at exactly the golden ratio. And this is just estimating it with a calculator program, but I could show you how to derive that algebraically if you'd like. This is what you would normally do. You may have learned this. By the way, we call this phi, Greek letter phi, but for the sake of simplicity, I'm going to call this x because you're so used to using x. You may recall from Algebra 1, if you took it in 8th grade, that if you have a over b is equal to x, you can also say that b over a is equal to the reciprocal of that, 1 over x. We're going to make use of that in a moment. You may also recall from middle school that you can split up fractions like this. A plus b over a is the same as a over a plus b over a. Alright? So all I'm doing is I'm taking this original blue equation and I'm rewriting it down here. I split up that fraction and I'm setting it equal to a over b. Alright, now what we can say, since I just called a over b x, I can call a over b x. That's the substitution property of equality. We're going to actually solve this thing right here in terms of x. A over a is equal to, I need some more room. A over a is equal to 1. b over a, we just set it over here, is the same as 1 over x. So I'm going to use the substitution property of equality there. I just changed b over a to 1 over x. And this is equal to x. So now I have everything in terms of one variable, x. This is a hard equation to solve, so what I'm going to do is I'm going to multiply this entire equation by x. So I'm multiplying both sides of the equal sign by x. X times 1 is x. X times 1 over x is x over x, which is equal to 1. And x times x over here is x squared. So we have this equation here, which you may recall is called a quadratic equation. If you never heard that word before, if you never learned how to solve them, that's okay. You probably shouldn't have. This quadratic equation, I can manipulate it a little, and I can get x squared minus x minus 1 equals 0. All I did was move both of these terms to this side of the equal sign. There's a way you can solve quadratic equations. I'm not going to get into that right now because it's just we're not there yet. So I'm just going to use a program that I wrote on my calculator. So I went into program, then just use this program that I wrote. And I can leave links in the description to how to program this in your calculator if you want to learn. If you want to learn more about solving quadratics by hand, I'll also leave a link for that video as well. So my leading coefficient is 1. My next coefficient is negative 1. So I wrote my program to work like this. You just type in the coefficients, and the final coefficient down here is negative 1. And it's going to give me my answer here. And what do you know? That non-extraneous answer at the top there, the 1.618033989, that's the exact golden ratio. So I really just solved algebraically for what is the ratio that you could set up this line segment in that way that I described before, and it happens to be that exact golden ratio. Again, there's so many cool things that you can learn about the golden ratio. People have been studying it for thousands of years. It shows up in ancient Greek and Roman architecture, Leonardo da Vinci's drawings. It shows up in nature a lot of times in the form of the Fibonacci sequence, and you could go ahead and Google the golden ratio and spend the next 5 days learning about it. But I'll leave that up to you. Thank you for watching, and I look forward to having a great year with you guys. Again, if you want to learn more about quadratics and what I did there to actually solve that, you could watch these videos, but really don't feel the need to. It's not on a quiz. We will learn about this towards the end of the year, like in late May, early June. Really looking forward to working with you this year, and I hope you enjoyed.